in hybrid in this location. It's my pleasure to introduce Lizzi Pitt. Lizzi completed her PhD in 2021 at the University of Bath in the Samba Center for Doctoral Training. She was supervised by Professor Chris Jennison and worked in collaboration with allocating at Roche. Lizzi has recently joined UCB, working in the Center of Excellence for Statistical Innovation, and she will be presenting her work on optimizing first-in-human trials via dynamic programming. Thank you, Lizzi. Thanks.
Going to choose from one of these dose levels at the end of the trial to be the dose that we recommend as the output. So I'm going to be working with six fixed dose levels, and say that the aim of this trial is to find the maximum tolerated dose. So the dose that corresponds to some certain rate of dose-limiting events occurring, so side effects that are considered too severe. And so the trial is conducted sequentially, so one cohort enters the study at a time. And the dose for the next cohort is chosen based on the response from the cohorts that we've got in the study so far. And the response is just a binary safety endpoint at this point, so whether each person experiences a dose-limiting event or not. And the dose escalation rule tells us, the study team, which dose to choose given whatever data they've observed so far. So when I'm talking about the design, what I mean is this dose escalation rule, so this thing that's dictating which doses we allocate during the study, and also the final decision at the end of the trial. So we've got the dose escalation rule plus the final decision making up our design. Yeah, so this is our key question. What's the optimal design for this first-in-human trial? Just like many things in life, we see that a one-size-fits-all approach doesn't necessarily work very well. And we need to find the design for a specific trial. We need to tailor it to those aims. We can define the aims of the trial by thinking about questions such as these. So what is the quantity that we're trying to estimate? As an example, that might be this maximum tolerated dose that I mentioned. It might be something else. How much weight should be put on avoiding safety events during the trial? What ethical constraints do we have, or do we want the trial to abide by? By that, I mean things like there might be limits on how much we can skip doses between, or how much we can increase the dose between cohorts, whether we can skip doses that we've got available. And also things like when we come to the end of the study and we're choosing the dose to recommend as a maximum tolerated dose, do we have some requirement that we've given it to a certain number of people during the trial? So we'll make sure that we've experimented at it and got some data there if we can recommend it. So once we've thought about our aims, we need to define them clearly with an objective function and possibly a set of constraints. So whilst I'm thinking about just a safety endpoint, just a safety endpoint, I've used a loss function. And this is just an example. So we might have a term based on how well we're estimating the maximum tolerated dose. So the dose we come up with at the end, how close is that to our target rate of dose-limiting events, which might be 20 or 30%, for example. And then we might also have a term based on the safety during the trial. So we can have some penalty term to penalize events that happen during the trial. And constraints, I just mentioned these, so things about like how much can we increase the dose by between cohorts, and constraints on our decision at the end of the study based on the data that we've collected. So once we've defined our aims with an objective function and set of constraints, we can use something called dynamic programming to find the design, so the dose escalation rule and final decision that is globally optimal with respect to those aims. So we can think of the trial a bit like a network. So each of these circles is representing a data set, so a state of the system, and we're gonna move through the trial. So this is cohort 1, cohort 2, and so on. And there's a number of paths that we can take through the trial or through this network based on the doses that we allocate to cohorts and also the responses that we observe. So to find the optimal design, we want to find the best choice of dose to allocate to the next cohort and to recommend at the end of the trial, given whatever data we've observed at whatever stage we're at. So essentially, we want to fill in all of these circles and suppose that this network is actually every possible data set that we could observe. So to do this, to find the rule that's globally optimal with respect to our chosen set of aims, so our chosen objective function and set of constraints, we're going to start with the simplest decision first. So that's starting at the final stage of the trial. At this point, we've observed all the data and we just need to choose which of our fixed set of doses we're going to recommend as the maximum tolerated dose to be optimal with respect to our aims, given what we've observed. So suppose we're at one of these final stage states, we are going to calculate the posterior expected loss associated with choosing each of the possible doses. So dose 1 through to dose 6, and then we will choose the dose that minimizes that posterior expected loss. And we will store that, and we'll store the decision, the optimal decision, and we'll also store the value of the posterior expected loss associated with that decision. And so we're gonna fill in all of these circles at the final stage. We're going to do that calculation for every possible data set that we could have at the final stage of the trial. And by data set, I can't remember if I said this, I mean the number of cohorts allocated to each dose level and the number of events observed at each dose level. So once we've filled in all the circles for the final stage, we step back to the penultimate stage of the trial. And the decision we have to make here, so suppose we're at this orange state, the decision we need to make here is which dose should we allocate to the final cohort to proceed optimally, given the data we've observed at this orange state, and the fact that we already know what the best thing to do is once we get to that final stage, because we've already calculated and stored that. So let's suppose that we consider choosing dose 1 from this orange state, and that could take us to the final stage states indicated by these orange arrows. So the posterior expected loss associated with, let's say we're choosing dose 1, given the data we've observed here and conditional on doing the best thing at the final stage, is a weighted average of the loss associated with the optimal decision at the states we could move to. So a weighted average of the loss associated with choosing dose 4 here, dose 6 here, dose 1 here, and I can't remember what's at the bottom because I can't see it now, dose 3. So, and those weights are given by the posterior probability of transitioning to that state. So that's considering choosing dose 1. Suppose instead we considered choosing dose 4, there'd be some different states that we could move to. Again, we take the weighted average and we do a calculation of this type for each of the possible choices of dose, so 1 through to 6, and then choose the one that minimizes that posterior expected loss, conditional on proceeding optimally, and fill in that gap. So let's say that dose 4 was the best choice here, and we would do similar calculation for every possible data set at this penultimate stage of the trial, and then we'd continue working backwards. So we're going to fill in all of these circles. The optimal rule then looks like the optimal choice of dose given whatever data we've observed so far at whatever stage of the trial. Yeah, I think that's the rule described. So I'm not going to go through this in detail, but I'm just going to briefly show what are called the Bellman equations for this dynamic programming problem, which is what I've just been trying to describe. So I'm indexing the stages of the trial, equivalently the cohorts, by J, and calling the data set xj. So one of those circles is this xj. So we're starting at the final stage of the trial, and this is our calculation for the posterior expected loss. So I'm using omega ji to mean the posterior expected loss associated with choosing dose I as the dose to recommend at the end of the trial at stage J, and this is calculated for each data set. So we evaluate the loss function at our chosen dose I, and underneath this we've got a model parameter which I'm calling A, and then we integrate that over the posterior given the data for the model parameter given the data xj. And then so we do that for each possible I, so 1 through to 6 in the scenario I've been describing, and then we store the minimum expected loss. So that's the loss associated with making the optimal decision from this state xj, and we store that as beta. So when we come back to the penultimate stage or any non-final stage of the trial, we need some way of describing those states that we could move to. So ones are those orange arrows or those pink arrows. And we also need some way of describing the probability of moving to each of those states. And then again, using omega ji now for the conditionals. So the expected loss associated with choosing dose I, but now we're conditional on proceeding optimally for the remainder of the trial. So we've got this weighted average bit here, and you can see here, this is a term where we're reading in that expected loss that we've already calculated. And we're integrating over the posterior given our current data. Yeah, and then again, we take the minimum and store that. So the other thing to note here is just that there's lots of integration going on, so that's relevant for the level of computation. Okay, so what I've just shown you is that dynamic programming can be used. Well, I guess I haven't shown you. I've told you without any evidence that dynamic programming can be used to produce optimal rules if you define your aims of your first-in-human trial with an objective function and possibly a set of constraints. Yeah, so the constraints would just, when I was saying we had those 6 doses, we would reduce that set if we had constraints based on the data we've observed. So as I alluded to a bit on the previous slide, we've got a 1 parameter model underlying this. So we're describing the dose response relationship with this model, which is, if you know it, it's the model from the O'Quigley et al. Paper introducing the CRM. There's a tangent there and some powers, but this is what it looks like. And key thing is just that a smaller value of A means that the drug is more toxic. So with our trial, our dose escalation scheme, essentially our data sampling method, we're trying to learn about this parameter A. And it turns out that given the observed data, our beliefs about the model parameter A can be summarized pretty well with a gamma distribution. So this means that we can take this collection of quite a lot of numbers, so the number of cohorts allocated to each dose and the responses that we've got on the left. So we've got 2 different examples, one where we've used higher doses and we're not seeing many events, and a more toxic scenario down here where we've only got to dose 2 and we've got lots of events. So first of all, we summarize. So given those data, we calculate the posterior for our model parameter given those data, and that's these blue lines, and the approximating gamma distribution is overlaid as the dotted line. So it's just showing that the fit is fairly good for 2 different scenarios, so 2 distinct things in this state space of posterior density functions for the model parameter. And why this is useful is because it means that we can take this collection of lots of numbers on the left and turn it in and represent that with just 2 parameters, the parameters that define that gamma distribution that approximates the posterior for the model parameter given those data. And that's useful because it means that we can plot the data. So that dynamic programming rule is giving us the dose to choose at every possible data set. So that's filling in that network. And that was a very difficult object to interrogate. There was no obvious way to plot that and really understand what's going on. And this turned out to be a way to get somewhere into looking at what the rule is doing. So what you're looking at here, each point on these plots represents data set, and it's plotted in terms of the parameters that define the gamma distribution that approximates the posterior given those data. And then the color is showing the optimal choice of dose given those data. So here we're looking at a sample of data sets from the final stage of the trial. So the choice is the optimal choice of dose to recommend as the maximum tolerated dose. And on the left-hand side of the screen, I've created the rule as if our only aim is to estimate the maximum tolerated dose well. So the loss function just has one term, which is based on, and we're trying to minimize the distance between the, so say that we're aiming for a 30% rate of dose limiting events. We want the maximum tolerated dose to be as close as possible to the dose that corresponds to a 30% rate of events. So yeah, and the rule looks something like this that we get. And then on the right-hand side, we've introduced a constraint that I can only recommend a dose at the end of the trial if I've actually used it. I think in this case, I said that I have to given it to at least one cohort in the study. And all I want you to see from this is just that this picture looks different to this picture. So this is highlighting that why we need to define all our aims up front. So if we had that rule that we can only recommend a dose if we've used it, then we can see that if we don't say that up front, we're not necessarily going to do that. So yeah, we need to define all our aims up front and then optimize with those in mind, because different rules, different aims lead to different rules. We can see this again if we step back to the penultimate stage of the trial. So now again, each point is representing a data set, and now it's from the penultimate stage of the trial. So I think in this case, it's after 8 cohorts out of a trial with 9 cohorts of 3. And on the left-hand side, so the color is now the optimal choice of dose to allocate to the final cohort. And on the left, again, I've just optimized with respect to an objective function that just contains an estimation term. And then on the right-hand side, I've introduced a penalty for events. So I'm trying to control the number of safety events that we see during the trial. And what we see here is that this puts a lot of allocation to the lowest dose level. So this kind of area of the plot is corresponding to very toxic scenarios where there are lots of events at high dose levels. So we probably wouldn't have these happening in real life anyway, but we're calculating it for every possible data set, so they're in our state space. Yeah, so this is just highlighting that different sets of aims lead to different optimal rules, and that's why it's important to properly think about the aims up front and then choose the trial design with those aims in mind so that you get one that meets those aims. Yeah, so we can also use this framework as a benchmark to help us answer kind of what if questions. So if, say, we've got that constraint where we can only go up one level at a time, well, what happens if we don't have that constraint? Do we do better with respect to whatever our aim is? We can evaluate the expected loss of a design. So if we simulate trials according to a certain rule and then evaluate the loss at the maximum tolerated dose that I'm choosing at the end of the trial, and then average that loss over the simulated trials. So these numbers are all from 1 million simulated trials. Yeah, then we can compare that loss. So this column is going to be as if our aim is just to estimate the maximum tolerated dose well. So we've just got that estimation term. And then on the right-hand column, we can compare the designs if our aim is to estimate maximum tolerated dose well, but also control the number of events. Yeah, so, and here I'm using the 3+3 design, which is just a rule-based design, the continual reassessment method, model-based design. DPA is what I'm calling the design that I've optimized just with respect to the objective function with the estimation term, and DPB is the rule optimized for this loss function with the penalty. So if our aim is just to estimate maximum tolerated dose well, this is the quantity for the best we can do. So the minimum expected loss is this 0.153, and what we see is that the CRM is actually performing pretty much just as well, and the 3+3 is. So yeah, and then if we bring in that aim to control for the safety events as well, the best we can do is 0.185, and in this case the dynamic programming design that's optimized for that rule outperforms the CRM. Another thing to note here is this 0.155. So this is where we've optimized, we've run the dynamic programming with the objective function that has the two terms. So it just shows that if you've got multiple terms in your objective function, then there's a bit of a trade-off. So we're not doing quite as well with respect to the aim of just estimating the maximum tolerated dose, but we're not losing that much. But yeah, that's the slight trade-off introduced. Yeah, so this is an application of dynamic programming to a problem with a large state space. So this table is showing that as we add another cohort of 3, so we increase the trial size by another cohort of 3, the number of possible states, the number of possible data sets increases pretty rapidly. And with the, so my implementation, we've been able to use that implementation of dynamic programming to produce a rule for a trial with up to 9 cohorts of 3 and 6 doses to choose from. But then we got into memory problems when trying to produce a rule for a trial with 10 cohorts of 3. Yeah, so most of the work here is, well, there's work because it's a large state space. Most of the work going on is numerical integration. And I guess, so there was quite a lot of work around getting a numerical integration scheme a better one for this problem, but that kind of goes into getting that initial implementation to work for a trial of 9 cohorts of 3. And then once to go further, we have a separate issue. So can we reduce the overall amount of work required to compute the optimal rule? Well, what matters for decision making is that posterior density function for the model parameter A given the data. So we convert our data that looks like this into the posterior density function. And what we find is that we end up with distinct data sets that lead to very similar posteriors. So I'm not showing you the data set, but these are 5 real posteriors from different data sets that essentially look the same. So if, actually don't even know if it's 5, I just said 5, there's some different ones. So if we consider the space of posterior density functions, then it suggests that we could sample from this space without losing information, because lots of things are essentially in the same place, or without losing information to a degree that matters. Yeah, so we want to find an approximation to the dynamic programming algorithm that operates on a sample of the state space at each stage of the trial. But previously, I told you that we are storing the decision at every possible state, that we've got to fill in all of these circles. So now what do we do when we're here at this orange state at the penultimate stage? We need to take our weighted average of the loss associated with this one, this one, this one, and this one. How do we know what the expected loss associated with the optimal decision at this question mark state is, as that's not in our sample? Well, consider the posterior expected loss of choosing be any dose, but let's say dose 4 at any final stage state. So what you're looking at here is, once again, each point represents a data set, but this time it's plotted in terms of the mean and the variance of the gamma distribution that approximates the posterior density function given those data, rather than the lambda and k that I had before. And the color is the expected loss associated with choosing dose 4. So that's that omega capital J 4. So this is the relationship that we want to model. We want to be able to, given a final stage data set, predict what the expected loss associated with choosing dose 4 is, given those data. And we want to do this for each of the possible choices of dose. So suppose we have a picture like this for dose 1 through to dose 6. And then we're going to model this relationship with generalized additive models. And that can be done pretty easily in R using Simon Wood's MGCV package. Yeah, so we wanted to fill in this question mark. So we've fitted 6 GAMs, one for the relationship for omega 1 through to omega 6. So we've got one for each dose. And let's suppose that this cross represents the data set at this question mark state. So then for this final stage, we're gonna use the models to predict the expected loss associated with choosing dose 1, dose 2, and so on, and then take the minimum. So we get 6 values, one from each model, and then we want the smallest value, which with this scale is the one that's the most yellow. So that turns out to be dose 6 that we fill in that gap with. Yeah, so then now we've filled in our gap, we can take our weighted average over the loss associated with these final stage states to get the loss associated with choosing dose 1 at this penultimate stage data set. And again, we have a calculation of this form for every possible dose. So if we say we want to choose dose 4, then we're going to have some other value that we need to fill in. So again, we'll use those 6 fitted models, read off the expected loss associated with choosing each of the doses and take the minimum. And then we can take our weighted average over those 4 values. So we've got a calculation like this for each of the 6 doses again, and then we take the minimum and store that. And this time we're just going to do this calculation for every state in our sample rather than every possible state. So the resulting rule when using this approximate version of the algorithm looks a bit different. It's just like those collection of models at each stage of the trial. So we've got 1 model per dose for each stage of the trial. Yeah, and so I told you I could implement the exact dynamic programming algorithm for a trial with up to 9 cohorts of 3. So we can use that as a gold standard to compare, see how good the approximation is. And we're looking at trials with 5 cohorts, 7 cohorts, then 9 cohorts, because we want to see that we're not getting approximation error that increases as we go bigger. So this is, I've used the objective function with both the estimation term and the safety term, that toxicity penalty. So these are the expected losses that we want to compare, and we can see that the approximation is conforming well. Well, we're getting the same result with 3 decimal places. And just to look at these other numbers a bit, so these aren't. As we've got more information, we'd expect the loss to decrease because we've got more information. But this isn't happening in this column because of the safety penalty. So we see that if we look at the standard loss column, which is just that estimation term, these do decrease as we get more information. But then this toxicity penalty, which is actually like some parameter times number of events, it's 0.004 times number of events. And I'm not going to do the arithmetic on the top of my head to work out how many it is, but this, so because we've got more people, we've got more events, even if the rate might not be increasing, but the absolute number is increasing, and that's why these are not necessarily decreasing. But yeah, so the key message here is that the approximation is good and that we don't have error increasing as we add a stage. We can also compare them visually. So again, these are like the first lot of dots that I showed you. So each point is a data set in terms of the parameters that define the gamma distribution that approximates the posterior, and it's coloured here by the optimal choice to recommend as the maximum tolerated dose, with the rule produced by the approximate version of the algorithm on top and the exact on the bottom. So these pretty much the same. There are some differences. That one's different. I did spot a different one the other day, but now I'm not sure where it is. Yeah, and if we look at the penultimate stage, then yeah, we've got a few more differences going on here, but they're broadly the same. But what's really important about the approximation is that it's considerably cheaper to run. So we're operating on a sample of the full state space, and this right-hand column is showing the percentage of the full state space that we're using to create this rule. So you can see that at that final stage, we're just using 0.3% of the full state space. Yeah, so this is considerably cheaper to run, and to put it into context, I think that the exact version of the algorithm to get a rule for 9 cohorts of 3 was taking about 6 hours on the university supercomputer. And I think for the approximate version, it took about 2 hours on my laptop, and my laptop's just nothing special. So yeah, I mean, those are not really comparable, but it's a laptop versus supercomputer and it's quicker. So yeah, we're getting comparable accuracy and for a lot less work. So yeah, performance is comparable, and that means that we can consider larger trials, so we can get to that 10 and further. I think I only went up to 10 in my thesis, but Sophia asked me to do more in my corrections, and I think it worked for 20. I don't think I tried more. Yeah, but what this also means is that we can consider adding an efficacy endpoint. So as soon as we add that second endpoint, we've got another dimension to the data, as well as counting the number of safety events on binary efficacy endpoints. So we need to count the number of efficacy events. A small amount of context, I think if we've got 5 cohorts, we have about 58,000 data sets in the whole trial for one endpoint. And I think it's like 24 million if we've got 2 endpoints. There's a massive difference. And so I could only implement the full algorithm for a trial with 4 cohorts of 3 when I had 2 endpoints. So the approximation comes in much sooner. Yeah, so the key question that we come back to if we're trying to extend this to a trial with a safety and an efficacy endpoint is, what is the aims? And this is a harder question when we've got the 2 endpoints. It's really important to think about what type of trial is going to follow. So not just to think about this trial as an individual, but to think about it as part of a broader development plan, as that's going to influence what the output of the trial should be. So it might not be the maximum tolerated dose anymore if we've got an efficacy endpoint. We also might not just want to output one dose. We might want to try and output an interval of doses. And that's going to affect what the outcome is, and also what the objective function is. And then we have the same type of questions as for the safety only case: how much emphasis should be put on subjects in the study not experiencing safety events? And you could probably say the same for having a positive efficacy response, although I'm not sure how much that would be focused on in practice at this early stage. But if we can come up with what our aims are and define those as an objective function, then the safety only methodology extends pretty easily to a trial with an efficacy endpoint as well. So we have the dose toxicity model like I showed you earlier, and then we have an equivalent model for the dose efficacy relationships, model those separately, and I'm assuming that those responses are independent. And then the key difference is really just that now our low dimensional approximation of that data set, of that state, is now 4-dimensional. So we have two parameters that describe the gamma distribution that approximates the posterior for the dose toxicity model parameter, and then 2 for the posterior for the dose efficacy model parameter. And so that means there's more terms in those GAMs. Yeah, so I can implement this. I've implemented the approximate dynamic programming algorithm for a trial with 2 endpoints, but the objective functions I used were really just for proof of concept of the methodology. I don't think they'd be useful in practice necessarily. So the thing that needs to come next with this for it to go further is really trying to think of what are the aims of a trial with 2 endpoints and trying to get some meaningful objective functions. And I think this needs to be done through looking at case studies and a lot of conversation. So I had a short 7-month postdoc working with Roche to try and do some of this. And I possibly naively thought that if we had a study that had finished and we had a protocol, that we'd be able to look at it, we'd be able to pick out the aims, and then with some work, we'd be able to turn those aims into an objective function. It's not very easy. You can't do that. The aims are not written in the protocol because usually the aim is something like explore the safety and tolerability of blah, blah, blah. And that's not precise enough for this because any of the objectives that I showed you different colored dots for could be an interpretation of that. So if you interpret it in a different way, you're going to get a different answer. And so in that, really, we ended up trying to think of, so rather than applying this to a trial, which is what I thought might be the output of that postdoc, it was more, okay, what are the questions we need to ask to try and elicit the aims? And I don't think we completely got the answer. There's definitely work to do, but that thing of what trial is coming next is definitely really important, because there's different ways the development program could go, and I think you'll want a different output depending on what that is. So I think pretty much everything. Oh yeah, so come back to this question. If you had a trial in mind, do you think you have a precise definition of what your aim is? If you can define the aims of a trial with an objective function set of constraints, then this framework allows you to find the optimal design for that specific trial with those aims, and also it could be used, that optimal design could be used as a benchmark, and you can use this framework to compare different designs. Thanks.
Any questions for Lizzi? Martin?
I thought that was very interesting, and I bet you get questions right up until 3 o'clock. So I'll ask something that's a little bit tangential. Can I ask about slide 51?
Oh, the numbers aren't showing. Oh, no. Oh, it's the one with the table of comparing them, right?
Yeah, you're looking at the approximation.
Yeah.
So yeah, again, this is tangential, but your results are pretty similar across the different number of cohorts. So is this for some people a way of justifying a considerably smaller sample size depending on the kind of penalty that you choose?
I've never thought about it like that. I think if you want to think about sample size, you need to bring that in as an explicit objective, that you want to have some term in your objective function that penalizes, probably penalizes adding an extra cohort.
Sure, but if all things were equal, if you want to minimize your loss, and you say, well, I could have 15 people and it's this loss, or I could have 27 people and the loss works out the same. you may be interested in going for a smaller sample size.
Yeah, I think I see what you're saying, but I think that because that sample size hasn't been explicitly stated, so it's going to be smaller because there's going to be fewer events because there's fewer.
Yeah, so I guess it is dependent on that in maybe a sort of uncomfortable way.
Yeah. So I think I wouldn't advocate for that. I'd say that if they wanted smaller samples, then you could put some sort of sampling term in here. Because yeah, this is fixed. I've fixed my trial size here. So I think, so it's not allowing for early stopping. And I definitely think that could be brought in.
It's optimizing for a given sample size.
Yeah.
Or maximum sample size.
Yeah. So yeah, so these, I don't think these should really be compared across each other, apart from seeing, for the purpose here, that the error isn't increasing. Yeah, I don't think we can be saying that the trial with 5 is better than the trial with 9.
Okay, sure. It's interesting. That's good.
Okay, so
Probably a question
Following has his hand raised online. Can you please unmute and ask your question? Hopefully we can hear you.
Sure. Can you hear me?
Yes.
Okay, thanks. Very interesting talk. I'm just coming at this from an optimization
Hold on, 1
point.
second.
Yeah,
Can't really
sorry,
hear you. We're just
where-
gonna try and turn it up.
Yeah.
Can I start again?
Yes, please.
Okay. Yes, thank you. Really interesting talk. I'm coming at this from an optimization angle. I was just wondering, from your objectives, is it possible at all? Is it very difficult to basically descalarize your objective function? Because I guess you have 2 terms in there. And I was wondering if it's possible to do as to produce an actual Pareto set, or is that too difficult to do?
Did you say to produce a feature set?
Pareto set, so where you don't put your the objectives into one scalarized function, but you just you're optimizing over multiple objective functions. So you, at the end, you get a Pareto set instead of a single solution.
I haven't tried that. I think so. Whether it's possible would depend on. So I think. So it depends on whether it's going to increase the size of the state space. If it's just one thing that you're evaluating once you've got the data at the end of the trial. Well, not one thing. So if it's just, if you can evaluate those 2 things and bring them into one number, then maybe. I think I don't know enough about what you're suggesting to know whether it would work, but
okay.
I think that's going to be the constraint. If it's increasing the dimensionality, then things get difficult. If it's just a different thing to evaluate at the end of the trial, then I think it could be possible.
Yeah, in this case, I guess so. In your case, you're calculating the mean standard loss and the penalty for this toxicity. You still just be evaluating those terms, but instead of trying to minimize on just the combined term, you're minimizing on both of those terms independently. So I wouldn't think it would increase the amount of computation, but I guess I think to actually produce the set of alternatives, you probably requires an actual multi-objective approach, but never mind.
Any other question from the audience?
No, sorry, the chat is just me asking people to raise their hand if they've got a question.
Can I ask a question about the when you're trying to combine safety and efficacy? I mean, first off, it's quite a lot to expect from a first time in humans trial.
Yeah, so it wouldn't be, we're not thinking about, efficacy is potentially the wrong word. So probably a biomarker that is suggesting an early indication.
Some indication of pharmaceutical activity.
Yeah, and more likely that it would be used for futility rather than for efficacy. So in the spirit of let's kill this drug earlier if it's not going to go anywhere.
So is there any kind of almost generic objective function that would make sense? Because the objective is exactly what you stated, right? To explore the safety and efficacy of the medicine at various doses.
So, I mean, I can tell you the objective functions that I did use. I just don't think they cut it. So we tried the ones I've implemented it with something that was so maximize probability of efficacy, and then so probability of efficacy minus probability of toxicity. So it's almost thinking about, okay, we want to maximize efficacy, but we want to penalize the probability of toxicity. We also thought about that you might want to, it might only be good if you were like safe enough and showing signs of efficacy. So having an indicator function that says probability of toxicity is less than 0.3 and efficacy greater than 0.5, and then increase like reward being greater than that lower bound, and for efficacy, is that the right around? Yeah, and reward being less toxic. So those were the things I tried. I don't think that they would quite cut it as summarising all the aims of a real trial. But yeah.
Okay, I mean, that's the kind of thing that I was thinking, that you're always trying to, you'll have some idea about what acceptable parameters are to move forward, and you want to increase your confidence within that range.
Yeah, so I think constraints would be part of it. So those, but you might not want to be like, it might not be so black and white. It might be that if, it's going to depend on the scenario, but if say we had 0.3 as the toxicity, let's say that the efficacy was like massive, then maybe we'd accept a bit more on toxicity, and then we'd need some sort of step function instead. But
I think it's what you said, which is here, efficacy is not likely to be your final, not a real endpoint, right? So you're almost looking at, I mean, suppose it's some kind of PK thing, so you're looking at like how much you can knock target down while having an acceptable safety profile. It feels like that you could probably, they'll have they may have some idea what's tolerable from a safety point of view, and some idea how much you have to knock protein down in order to have a realistic chance of an effect. So that it might be possible to pull something out. Yeah. So that's the kind of thing we're thinking about. And then in the extensions, we were more thinking about, so if you wanted to maybe output an interval of doses that would be like minimum efficacious and maximum tolerated, then you've not just got 6 doses, you've got some number of intervals at the end, which we haven't done it, but we think is fine, because it's just, in the approximate version, it's just more models. It's just like having a wider set of doses, they're just different. And it's only a change at that final stage, and what you're averaging over at the penultimate stage, then it would go back to being the same. What was my point? But yeah, then you're thinking about, how do I weight these intervals against each other, or rate these intervals against each other? I don't have the answer. So like some sort of contours, maybe, if you've got that space of probability of efficacy, probability of toxicity, it's just not immediately, or even not immediately obvious how you'd rate those. So we actually got a bit further thinking about what was the scenario? It was, let's say that we want to take forward 2 doses, and one is going to be that ceiling that we can't go above. And then there was a scenario that one might be, so say that the regulators wanted to, say you're saying this is the dose, and the regulators come back to you with the question of, how do you know you can't go lower? So you want to have tested basically a dose that doesn't really work, like a dose below the one you're recommending.
so that you have some of that evidence. So then your objective is something about having this ceiling and this, what did I call it, like the highest non-efficacious dose or something like that. And you can start like building constraints on what each of these things should be. So like this top one has to not be too toxic. So probably this toxicity less than whatever your, let's say 0.3. And you want this one to not be too efficacious now. And you can start building things up with constraints like that. But yeah.
The only other thing that springs to mind is if you were fitting a dose response model for later stage, you might fit something like an Emacs model. And if you were, so I'm thinking that you might attempt to minimize the variance.
So, I mean, this isn't going to immediately transfer to more parameters because more parameters going to increase. Well, I mean, it means you've got two-dimensional integrals everywhere. So actually, with someone coding it in C rather than R, maybe it is possible.
Okay, well, last question, now shut up. Would it be a terrible idea to replace the gamma by a Gaussian distribution? Would that help?
I mean, you've still got two parameters, right?
Yeah.
But you wouldn't be, the Gaussian's not stopping it at 0. That's not the right word, but you know what I mean.
I know what, yeah.
I don't know, haven't tried. I think that was specific to this model and this problem. So if you were going to change the model, you'd need to change that. Yeah, it's basically, in theory, this would work as long as you have a low dimensional approximation of your state space and like insert low dimensional approximation. But I obviously haven't tried anything other than what I've done.
Can I ask you one probably final question unless we get another one? Would you mind going to slide 34? I think something that you're saying that I really like is this idea of fixing an objective or a set of objectives and then comparing designs according to how well they do with this objective. Because I think something that in many stages of trial we do is the opposite. Just compare lots of designs and then realize there are trade-offs and then try to choose based on that. So I think I really like that. But given that perspective, I'm going to do a question difficult, just like the one Martin did. One could take from these kind of results that, oh, well, the CRM doesn't do very bad in terms of the final decision, at least, or the final value. But something that I found really interesting from the thesis was that even if DP does seem to make the same final recommendation, so the objective or incorporation of an objective might not having too much impact in the final outcome of these two models. The way the dosing was done in the trial was quite different in the dynamic programming than in the CRM.
Yeah, so I think that is where the objective function comes in. So if your objective function is only about that final decision, then it's really like you're saying, I don't care what happens in the trial. So they're equally good because based on your aim that you've stated, they are equally good. So yeah, I think the case was that the dynamic programming tended to get to this same output at the end, but largely dosing at lower levels. And it makes sense because the CRM is targeting that, is trying to dose as many as possible at the maximum tolerated dose. So that's where if you want to control something about the dosing during the trial, you need to put that in your aim, and that's where this one came in that says, and this then pushes the allocation during the trial to, well, lower dose levels or safer ones, and it's a parameter, so you can play with how much you penalize events. If you put the parameter too high, then obviously everyone gets given the lowest dose.
I think that also motivated the problem of would a dose, a final recommendation that has not been tried enough in the trial be accepted.
Yeah,
If you were to use the dynamic programming with that objective, you could be in a situation in which your final recommendation has not been tried at all, or has been tried in just one cohort.
yeah. So I was getting these bar graphs of like which doses have been allocated and seeing that it was always recommending dose 6, but it hadn't given it to anyone. So that's why we added that into the objective function to
Yeah,
account
that's,
for that
that's hidden in
problem.
this comparison. It's a
Yeah.
very subtle difference. The final decision is the same, but the way to get to it is different.
But you'd accept, if a dose was in the middle of two doses that had been tried, you might be okay with it.
Yeah.
But if it's higher than anything you've tried.
I think it was probably higher, but I'm not.
It was higher,
It's
yeah.
higher.
But I think you could put that as a constraint that, yeah, it doesn't. Yeah, so I said that it had to have been used, but alternatively, you could say make the constraint that you can't choose higher.
Yeah, okay.
I think I had a hypothesis that I had to do that exploring the target from below. That's what DP is doing, rather than exploring it from above. But the CRM seems to be doing that, and yeah. Well, if there are no more questions in the remote audience and no more questions in the in-person audience, shall we thank Lizzi and a lot of claps.